Calorimetry is a technique that's used to measure the amount of heat involved in chemical or physical processes. And a calorimeter is a device that's actually used to measure the amount of heat that is either absorbed or evolved in either of those processes. In this section, we're going to learn different types of calculations involving calorimetry. Before we start, we have to understand a little bit about the system and the surroundings. When we describe the system, we're usually talking about our chemical reaction, which would be our flasks and our contents inside of them. Our surroundings are everything in direct contact with our flask. And the universe is everything, meaning the system plus the surroundings. When we consider heat transfers, heat will usually transfer from the system to the surroundings or from the surroundings to the system. We can track the heat flow by understanding some of the laws of thermodynamics. There are three different types of systems. Open systems, where heat and matter can both transfer. This would be like a beaker open with water in it. Eventually the water can evaporate. Heat can cause that evaporation, and the level of liquid in the beaker would eventually lower. A closed system, which would be like a beaker with a top on it. Heat could still transfer between the system and the surroundings, but because the beaker has a top on it, the matter level will never get lower inside. Therefore, matter cannot transfer. And isolated systems, where no heat or no matter can transfer between them. This would be like a thermos. If you were to fill a thermos with hot coffee, we would hope that the thermos would stay hot and all the coffee would stay inside. The system would be isolated from the surroundings in this case. If we imagine that we have an insulated container that is a perfect isolated system, and we did a reaction in there, and the system gave heat off to the surroundings, and we measured the temperature of the reaction initially and then finally after the reaction was completed, we would see that the temperature increased of the surroundings. This is an exothermic reaction, one where the system releases heat to the surroundings. And if the exact opposite happened, where the system ended up gaining heat from the surroundings, and we measured the temperature of the reaction in our isolated system before and after, we would see that the temperature of our surroundings went down after the reaction took place because some of the heat was absorbed by the system. This is an endothermic reaction. For an exothermic reaction, the sign on our heat or our Q is negative. And on an endothermic reaction, the sign on our Q is positive. The signs just mean if it's endothermic or exothermic. They only tell us the direction of heat flow. There are two different examples of calorimetry problems that we'll study in this chapter. The first ones are constant pressure calorimetry, which often take place in something called a coffee cup calorimeter, which is simply two nested styrofoam cups that have a reaction mixture inside, a stirrer to mix the reaction, and then a thermometer to take initial and final temperatures. These are under constant pressure because they're taking place in the open atmosphere in a laboratory. The constant pressure is the atmospheric pressure all around us. Another type of calorimetry calculation can be done using a bomb calorimeter. This is called constant volume calorimetry, and it's usually used for reactions that produce a lot of gases. It's also much more accurate than our coffee cup calorimeter. The bomb calorimeter makes it so the volume of the bomb is always the same. It's never changing, but we can see pressure changes inside of there from gases being formed. For reactions that occur in solution and can operate at constant atmospheric pressure, a coffee cup calorimeter is a simple device to use to set up an isolated system. We're assuming that all of the heat from the reaction stays inside of the calorimeter and none of it is lost to the styrofoam cups or to the surroundings. If we can measure our temperature before and after a chemical reaction or process, we can figure out how much heat was absorbed or evolved from that process. Remembering the first law of thermodynamics that says that energy cannot be gained or lost. It can only change forms. We can track the direction of heat flow. The heat lost by one object must be the heat gained by the other, only equal and opposite in sign. We use positive Q to represent heat being gained. We used negative Q to represent heat being lost. If we have two different things that we're transferring the heat between, we'll call them Q1 and Q2. The sum of the heats between both of those must add to 0. That's the law of conservation of energy. And if we set them equal to each other, we can see Q1 equals Q2, but they're opposite in sign. This will be our setup for tracking heat flow between two different things. A sample of iron was heated to 110 degrees Celsius and then placed in 150 grams of water at 25 degrees Celsius in an insulated cup. The equilibrium temperature of the water and iron was 25 degrees Celsius. What was the mass of the iron? So we have a situation where initially we have our insulated cup and we have some water in here. We have 150 grams of water inside of our cup, and it's initially at 25 degrees Celsius. We have a block of iron, and we know that our iron was heated up first to 110 degrees Celsius, but we don't know what the mass of our iron was. That's what we're going to be trying to figure out. What is the mass in grams? Our iron that was hot was thrown into our cold water. Our picture then looks like this. We have our insulated cup, and we're going to have our hot iron in there. And eventually, after those two are together, they will come to the same temperature. It says the equilibrium temperature of the water and iron was 27 degrees Celsius. So the iron lost heat and the water gained heat. This is called thermal equilibrium. Where two bodies that are in contact over time attain the same temperature. So we know our T final of the water and the metal is both going to be the same at 27 degrees Celsius. We can use the fact that the heat that was lost by our iron will be equal to the heat gained by the water. Those two are going to be equal and opposite in sign. So that means that Q of our iron will be equal to Q of our water. And we put a negative sign out in front of the Q for our iron because the iron is giving off heat to the water, and the water would be gaining it. So we have everything we need here to determine the unknown mass of our iron. Negative M sub Fe, mass of our iron, times C sub Fe, which will be the specific heat of our iron, times delta T will be equal to the heat gained by our water, which can be calculated by the mass of our water, times the specific heat of our water, times the change in temperature of our water. Reminder that delta T always equals T final minus T initial. In this case, we're determining the mass of our iron, so we're going to be solving for M sub Fe. If we isolate and solve the mass of our iron, that'll be equal to the mass of our water times the specific heat of our water times delta T divided by negative the specific heat of iron times our delta T for the iron. We have to check our units and make sure everything is going to cancel. Specific heat is in units of joules per gram degrees Celsius. So that means that our temperature changes have to be in degrees Celsius and our masses have to be in grams as well. The mass of our water was 150 grams. The specific heat of water is 4.184 joules per gram degrees Celsius. You would look that up on your specific heat chart. The temperature change, T final minus T initial, For the water, the final temperature was 27 degrees Celsius and the initial temperature was 25 degrees Celsius. Divided by, we have our negative out front still. Our specific heat for iron is 0.4498 joules per gram degree Celsius. And our change in temperature for our iron, the final temperature was also 27 degrees minus the starting temperature of 110 degrees Celsius. And you can double check that your units are all going to cancel. Our grams cancel here, our degrees C cancel here, our joules cancel on the top and the bottom, and our degrees C cancel on the bottom. We're left in units of grams, but it's 1 over grams and it's in the denominator, so that's the same as having just grams in the numerator. And we can solve for the mass of our iron, which should come out to be about 33.6 grams. The 50 grams of an unknown metal was heated to 200 degrees Celsius and placed in a calorimeter containing 100 grams of water at 30 degrees Celsius in an insulated cup. Following the addition, the temperature of the water rose to 46.5 degrees Celsius. What is the identity of the metal? If ever we're solving for the identity of an unknown, that means that we're going to find the specific heat of that unknown and then compare it to our chart in order to identify it. Here we have another example where the heat that is lost by our metal will be the heat that's gained by the water. So we're going to have those equal and opposite in sign. So the negative would technically go out in front of the metal, but it can go on either side and the arithmetic will still work out as long as you have one negative and one positive. That would mean that negative Q metal is equal to positive Q H2O. We can use our formula Q equals MC delta T for each of those components, the metal and the water, in this case to figure out the specific heat of the metal. So negative M metal, specific heat metal, times delta T is equal to the mass of the water, the specific heat of the water, times the change in temperature that occurred. If we rearrange and solve for C sub M, that'll be equal to mass of our water, specific heat of our water, times delta T, divided by negative mass of our metal times delta T, change in temperature of our metal. Our mass of our water, we were told was 100 grams. The specific heat of our water is 4.184 joules per gram degrees Celsius. Our temperature change of our water, that's going to be our final minus our initial. The final temperature of the water was 46.5 degrees Celsius minus our initial temperature, which was 30 degrees Celsius, divided by our mass of our unknown was 50 grams times the change in temperature. Since the metal and the water will be together, they will both attain thermal equilibrium. That means that the final temperature of the metal is also going to be 46.5 degrees Celsius minus the initial temperature, which was 200 degrees C. If we solve for C sub M, we should get 0.899 joules per gram degrees Celsius. And looking at our specific heat chart, that matches up to our unknown metal being aluminum. The last two examples looked at the heat transfer between two bodies of different temperature, one with a high kinetic energy and one with a low kinetic energy. We can use the same concept in order to determine the heat of a reaction. Heat could either be produced or consumed, and that will depend upon the sign we get for our Q. So the heat of the reaction will be equal and opposite in sign to the heat of the reaction mixture, often called the heat of the solution. The reaction of HCl and NaOH solutions is rapid and exothermic. In one experiment, a student placed 50 milliliters of 1 molar hydrochloric acid at 25.5 degrees Celsius in a coffee cup calorimeter. To this was added 50 milliliters of 1.5 molar sodium hydroxide solution, also at 25.5 degrees Celsius. The mixture was stirred and the temperature quickly increased to 32.2 degrees C. Assume both solutions have a density of 1 gram per milliliter and a specific heat of 4.184 joules per gram degree Celsius. What is the heat of the reaction in kilojoules and in kilojoules per mole of acid? So what do we have going on? We have an acid-base neutralization reaction taking place where hydrochloric acid is being mixed with sodium hydroxide to produce a salt, which will be sodium chloride, and water. We know we're starting with 50 milliliters of HCl and 50 milliliters of sodium hydroxide. By being told that the solutions both have a density that's the same as water of 1 gram per milliliter, we can assume that our 50 milliliters is also equal to 50 grams of the sodium hydroxide and the hydrochloric acid. So we know the mass of both of our starting solutions. We also know that they were both initially at the same temperature, 25.5 degrees Celsius. When they were mixed together and the reaction was performed, the temperature increased to 32.2 degrees Celsius. We can say that the heat of the reaction is equal to, and opposite in sign, the heat generated by the solution. The heat of the solution can be calculated by taking the mass times the specific heat times the change in temperature for our total two reagents, which would be the HCl and the NaOH. The mass is going to be 50 grams of HCl plus 50 grams of sodium hydroxide. So we're going to have a total of 100 grams. The specific heat is that of water, 4.184 joules per gram degrees Celsius. Because these solutions are aqueous, meaning they're in water, and the amount of solute present is small, we can assume that the density and the specific heat is the same as water to make some simplifying assumptions. And our T final minus our T initial, the T final was 32.2 degrees Celsius, and our initial was 25.5 degrees Celsius. Our grams is going to cancel, and our degrees Celsius is going to cancel, and so our heat will be in units of joules. So the heat of the reaction, or Q reaction, will be equal to negative 2,803 joules. And a joule is a pretty small amount of energy, so often it's reported as kilojoules. If we were to divide by 1,000, we would have 2.8 kilojoules of energy that were released when this acid-base neutralization took place. Often it's also recorded common to find the kilojoules per mole of the limiting reactant. And in this case, the acid is the limiting reactant because it's present in a 1 molar amount, whereas the sodium hydroxide is present in a 1.5 molar amount. And since we have 50 milliliters of both of them, we can see that there's going to be a lesser amount of moles of HCl. We can use the formula molarity times the volume in liters to calculate the number of moles of acid. Our molarity of acid was 1 mole per liter, and our volume of HCl was 50 milliliters or 0.050 liters. Our liters will cancel, and our number of moles will be 0.050 moles of HCl. If we take the energy we calculated in the first part and divide by the moles, we can describe how much energy is produced per mole. Negative 2.8 kilojoules divided by 0.050 moles of our acid will give us approximately negative 56 kilojoules per mole. And no matter what acid-base neutralization you look at, if you were to write the net ionic equation for any strong acid, strong base neutralization, they all end up dwindling down to aqueous hydrogen ions, combining with aqueous hydroxide ions to form water. Therefore, if the acid and base are reacting in a 1-to-1 ratio, the energy in kilojoules per mole for any acid-base neutralization that fits that will end up being exactly the same. Let's try another example. When 100 milliliters of 0.2 molar sodium chloride and 100 milliliters of 0.2 molar silver nitrate are at 21.9 degrees Celsius are mixed in a coffee cup calorimeter, the temperature increases to 23.5 degrees Celsius as the solid silver chloride precipitate forms. How much heat in kilojoules is produced by this precipitation reaction? And how much heat in kilojoules per mole? So here we have two aqueous solutions, sodium chloride and silver nitrate being mixed. We can predict the products using double replacement. We're going to form silver chloride, which if we look at our solubility rules will be a solid precipitate that crashes out. And we're going to form sodium nitrate, which will be aqueous. So we're trying to figure out how much heat is generated when this solid precipitate forms. We are told that we have 100 milliliters of sodium chloride solution, and we have 100 milliliters of silver nitrate solution. Because these are solutions and they're in water, we can make the simplifying assumption that we have a density of 1 gram per milliliter. Therefore, our 100 milliliters becomes 100 grams of sodium chloride solution, and our 100 milliliters for silver nitrate also becomes 100 grams. The heat of our reaction can be calculated by taking the heat of our solution, and it'll be opposite in sign. The heat of our solution will be negative MC delta T. The mass total of our solutions is going to be 100 grams plus 100 grams for both of them, so 200 grams total, times our specific heat of water, that's our second assumption we can make, 4.184 joules per gram degrees Celsius, times our T final minus our T initial. The temperature increased, so we know this was an exothermic reaction, 23.5 minus 21.9 degrees Celsius. Our units of grams cancel and our units of Celsius cancel. Our heat is in units of joules. And the heat of our reaction is equal to negative 1.34 times 10 to the third joules, or negative 1.34 kilojoules if we divide by 1,000. The negative sign out in front tells us that this is an exothermic reaction, one where heat was given off. So heat would be a product of this reaction. If we want to calculate our heat in units of kilojoules per mole, we can figure out our number of moles by taking the molarity times the volume in liters to get the number of moles. And since we have sodium chloride and silver nitrate both being the same concentration, and we are using the same volume of both of them, we can pick either one. So our molarity is 0.200 moles per liter times our volume, which is in liters, 0.100 liters. Our units of liters cancel, and our number of moles is 0.02 moles. Taking our heat that we calculated in part 1, negative 1.34 kilojoules, we're going to divide by our 0.02 moles, and that'll give us negative 67 kilojoules per mole. So that's how much heat is released per mole. Whereas at the top, the negative 1.34 kilojoules is how much heat is released when 100 milliliters of each of them is mixed. When solid ammonium nitrate dissolves in water, the solution becomes cold. This is the basis for an instant ice pack. When 3.21 grams of solid ammonium nitrate dissolves in 50 grams of water at 24.9 degrees Celsius in a calorimeter, the temperature decreases to 20.3 degrees Celsius. Calculate the value of Q for this reaction and explain the meaning of its arithmetic sign. In this example, we have a solid salt, which would be ammonium nitrate, that we're dissolving in water, and so it'll dissociate into its ions. We'll get ammonium ions that are aqueous, plus we will get nitrate ions that are also aqueous and solvated by water. We're being told that when ammonium nitrate breaks up in its ions, the solution becomes cold. Therefore, the temperature decreased. So this is an example of an endothermic process where energy or heat would end up being a reactant instead of a product, like in the last two examples we saw. The heat of the reaction will be equal and opposite in sign to the heat of the solution. So we'll have negative MC delta T again. The mass that we plug in is going to be the total mass. We have to include the mass of our solid ammonium nitrate as well as the mass of our water. So we had 50 grams of water and 3.21 grams of our solid. So we're going to have 53.21 grams for our mass. Our specific heat, we still made an aqueous solution, so we still can assume it's the same as water, 4.184 joules per gram degrees Celsius. And our change in temperature, we still want to take our T final minus our T initial, only this time our T final is 20.3 degrees Celsius and our initial is 24.9 degrees Celsius. So 20.3 minus 24.9 degrees Celsius. The heat of our reaction is going to be a positive value this time, and we'll get 1.02 times 10 to the third joules, or we can say 1.02 kilojoules if we divide by 1,000. This positive sign for our heat that we got tells us that it was an endothermic process, whereas before we calculated Q and we had a negative value, and that told us that the process was exothermic. So if you have a process or a reaction and the reaction releases heat energy, it'll be exothermic and your Q will be negative. And if you have a process or a reaction and it requires heat energy, your Q will be a positive value. So that's what the arithmetic sign of Q tells us. In the last few examples, the reactions took place inside of a coffee cup calorimeter. A coffee cup calorimeter is assumed to be an isolated system, but in reality, it's not a perfect isolated system. Some of the heat from the reaction could be lost to the surroundings. If we need a much more accurate depiction of the heat either absorbed or evolved in a chemical process, we can use something called a bomb calorimeter. When we look at a bomb calorimeter, the heat that could be absorbed by the bomb is actually figured out and added to the heat gained by the solution. So we take both of those components into account to get a much more accurate representation of how much heat a reaction is either giving off or absorbing. A bomb calorimeter is an instrument used for measuring heats of reaction. It operates at a constant volume. We have a very heavily insulated vat that's surrounded by water. The water is what we would measure the initial and the final temperature of the reaction of. We would also figure out how much heat energy actually gets absorbed by the bomb itself by calibrating it first. The reaction takes place inside of the bomb where there's an inlet in order to combust a sample. This is really good for measuring reactions that produce a large amount of gaseous products. Because we're operating at constant volume, none of the energy will get converted to work. So energy could be released in the form of heat or work when we're operating at constant pressure, such as in a coffee cup calorimeter. But when we're restricting to being at constant volume, all of the energy released will be in the form of heat. The bomb calorimeter first is calibrated by us determining or being told what the heat capacity of the calorimeter is itself. And if you remember, heat capacity is not the same as specific heat. Its symbol is a capital C, rather with specific heat, it's a lowercase c. So the heat capacity of our calorimeter we'll have to know in order to determine a much more accurate depiction of the heat from a reaction. When 3.12 grams of glucose is burned in a bomb calorimeter, the temperature of the calorimeter increases from 23.8 to 35.6 degrees Celsius. The calorimeter contains 775 grams of water, and the bomb itself has a heat capacity of 893 joules per degree Celsius. This is going to be our C sub cal, the heat capacity of our calorimeter. How much heat was produced by the combustion of the glucose sample? The heat of our reaction will be equal to, and opposite in sign, the sum of the heat of our water change plus the heat from the bomb itself, where we need to use the heat capacity of our calorimeter. So in order to calculate the heat of our reaction, we need to use the mass of our water times the specific heat of our water times the change in temperature of our water, plus we have to determine the heat that was absorbed by the bomb itself. For the bomb calorimeter, we know the heat capacity, which is in units of joules per degree Celsius. So we have to take the heat capacity of our calorimeter and we have to multiply by the change in the temperature in order to get the energy that was absorbed. So negative times the mass of our water, which was 775 grams, times our specific heat of water, 4.184 joules per gram degrees Celsius, times our delta T. Our final temperature was greater, 35.6 minus 23.8 degrees Celsius, plus the heat capacity of our calorimeter was 893 joules per degree Celsius. And if we multiply by our delta T, that's going to be the exact same delta T as the water, 35.6 minus 23.8 degrees Celsius. Our grams will cancel, our degrees C will cancel, and on the right-hand side, our degrees C cancel. We'll be left with units of joules here and units of joules here, so we can add them together at the end. So summing both components together, we end up with the heat of our reaction, which is negative 4.88 times 10 to the 4th joules, or we have negative 48.8 kilojoules. That would be the energy that is released when specifically 3.2 grams of glucose is combusted. So we didn't actually have to use that in our calculation. If the problem had asked us for kilojoules per mole, then we would take our 3.2 grams of glucose and convert it to moles using the molar mass and divide by that amount. When 0.963 grams of benzene is burned in a bomb calorimeter, the temperature of the calorimeter increases by 8.39 degrees Celsius. The bomb has a heat capacity of 784 joules per degree Celsius and is submerged in 925 milliliters of water. How much heat was produced by the combustion of benzene? So our heat of our reaction will be equal to, an opposite in sign, the heat from the water in the bomb plus the heat that the bomb itself is absorbing. So we're going to have negative the mass of our water times the specific heat of our water times the change in temperature, plus we're going to have the heat capacity of the calorimeter times the change in temperature. Our heat of our reaction will be negative. We have 925 milliliters of water for our volume, which will be the same as our mass because water has a density of 1 gram per milliliter. Our specific heat is 4.184 joules per gram degrees Celsius, times our delta T. By them telling us that the temperature of the calorimeter increased by 8.39 degrees Celsius, that's them telling us our delta T. So we actually don't have anything to subtract in this example. We just get to plug in 8.39 degrees Celsius. Now we need to add on the heat absorbed by the calorimeter itself. The heat capacity was 784 joules per degree Celsius, and we need to multiply by that change in temperature, 8.39 degrees C. Check to make sure our units cancel, our grams cancel, our degrees Celsius cancel, and on the right-hand side, our degrees Celsius cancel. So we're going to have joules plus joules. And the heat of our reaction, how much heat was released when the benzene was combusted? So negative 3.90 times 10 to the 4th joules, which is equal to negative 39 kilojoules. And that negative sign out front tells us the reaction was exothermic, which we would expect because the temperature increased of that reaction. Bomb calorimetry is used in order to determine the energy within food. So since it's much more accurate than using something like a coffee cup calorimeter, and we have constant volume, so we don't have to worry about generating gases, we can take a sample of food, blend it, freeze dry it, make it into a powder by grinding it up, and then form it into a pellet where we know the mass. If we put it inside of the bomb calorimeter and combust it, we can determine the energy change of the water after we calibrate the bomb calorimeter itself. And this is how we would determine the nutritional content of food. If we were to look at our food label and we see that something has 250 calories, we can break down the number of carbs, fats, and protein within those calories. 1 lowercase c calorie equals exactly 4.184 joules. 1 calorie on a food label, which is written with a capital C, is equal to 1,000 calories or 1 kcal. Protein is 4 calories per gram, carbohydrates is 4 calories per gram, and fat is 9 calories per gram since it's much more energy dense. And if we were to look at how much fat and how many carbohydrates and how much protein is in our sample and multiply by the appropriate calories per gram, those should sum up to the overall calories that we see at the top of our label. We would be able to also determine this energy from our combustion in the bomb calorimeter itself.